Welcome you all. Today we will start with concepts of soil water potential. Earlier I have also discussed what is soil water potential and the synonymous terms used with it, like soil water tension, soil water suction. Today we will discuss in detail about soil water potential. So, as you have seen, this soil water potential, we can say rather, this is nothing but the energy status of the water. Okay, this your water retention, movement, evaporation, or evapotranspiration, all these processes actually mainly the function of your energy status of the water in soil. So, you can see with that. This is a tree, this is the soil surface, this is your root structure, and you can say if here the potential or rather energy of water in terms of bar is -3 bar. Okay. Now in terms of your root structure, I can say this is your soil, and in your root I can say it is almost -3 bar, and at your stomata or I can say leaf structure, the potential now becomes -30 bar. In atmosphere I can say the energy status of potential of water reaches to -300 bar. Now you can see there is gradual decrease of water potential, or we can say energy status. So as the water potential decreases, here in minus terms you can see here the highest water potential compared to this, we can say SPAC, soil plant atmosphere continuum. This is a continuous process. Rainfall happens, now water will be free energy flow will be there, then water content will decrease, it will acquire some energy state. Now as here dry state comes, when the water needed for plant to grow, it will take from soil. This way, this is a continuous process. You can say soil plant atmosphere continuum. We will discuss that in detail also in next further classes. You can see here how the potential is decreasing and movement of water happens like this way. In soil also, I have discussed if this is a profile, if think this is a point A, this is point B, or rather this is point C, point D. Okay, the highest water potential is at I can say C, and the lowest is at your D. So the water movement will happen from C to D, and compared to A, B has higher potential. The water movement can happen this way. Okay, this is nothing but the energy state. Where the energy status will be higher, the water movement will happen from higher energy to lower energy state. This is universal concept also. We know always water movement happens from higher energy state to your lower energy state. So this energy can be of two types. We know one is your kinetic energy, another one is your potential energy. Why kinetic energy developed? Due to the movement of water. But in terms of soil water, we can say the movement is very low. Okay, so we normally neglect this. We normally neglect kinetic energy, but we measure the soil potential, water potential, all of these energy terms in terms of your potential energy. So potential energy what? This is, we can say, energy of a body. This we can say energy of a body. That's maybe water body or anybody. This is universal concept. Energy of a body by virtue of its position. By virtue of its position in a host field. Okay, we can see potential energy due to the position on the soil, different zones, and in route to plant and atmosphere, different positions of the water, we can say the energy it acquires. And there is presence of some force fields. Now we will discuss what are the force fields which force to reduce its energy. These force fields, if the force fields are not there, the energy will not be reduced. This will be in a free energy state. We will be acquiring maximum energy, we can say. Now, if I say, as I have discussed also, this is your soil surface. This is soil profile. I have discussed there are 3 zones, and we say this is your groundwater zone. This is your groundwater zone. Here there will be no effect of any forces. So the water here acquires maximum free energy. You can say it acquires maximum free energy. And we can say it also as pure water. There are no forces acting except the atmospheric pressure. And here you can say your energy status is maximum. Okay, and the potential of water is 0. Now, as water enters through the soil through capillary. For your understanding, I am drawing it straight, but it is actually not straight. We have seen how the soil pores are remain. Like you can say, this is a large macropore. This is connected by small interconnected micropores. Okay. This way actually water enters from the saturated zone to unsaturated zone. I have said already that unsaturated hazard zone is the most important zone where because of that only the water movement happens. So if you see different type of forces, we know there are presence of soil matrix. I have already discussed what are the soil matrix. Soil matrix are simply we can say sand, silt, clay, the primary particles by which soil is made up of. We can say that are the soil matrix, or rather I can write it as soil solid. Okay, and when the water comes to capillarity, now water is coming to capillarity. Okay, now it will adsorb on the surfaces of this soil matrix. Why? Because of your adhesive nature of these solid particles have adhesive nature towards the water, and water also possesses some properties like hydrogen bonding, your van der Waals forces of attraction. That's why the water film will be created. And when more amount of water after adsorption on the surface, adsorption actually occurs on the surface. Then when more water comes, it will form a thick film. It will form a thick film. Now, after forming a thick film, now it will enter also into the your capillary pores also. Like this way, you see, and here the major process of obstructing, I can say that is one your matric forces. Matric forces. It is very clear now. We are discussing different potentials. So, as the force exerted by the solid particles or soil matrix, we can say this is the matric force. Okay, the potential that will develop from this matric process will be the matric potential. We will see. Now, there will be also presence of some in saline soil. You just see some saline soils are there. there will be presence of some cations that will also absorb some water. This is normally happens in saline soil. Then another type of force we can write here is your solute force or osmotic force. We have already discussed that in saline soil the presence of more number of cations creates the problem. Although the physical condition is good, because of osmosis the plant growth is affected. So these are created in saline soil. Now another one force which is universal, we can say another one force which is acting here and there, it is, we can say, gravitational force, which pulls all the object towards the center of earth. Gravitational force. And as water is there, so we can say there is also pressure force there, we can rather say pressure potential. This pressure potential in terms of Matric forces, we can say your pressure potential because of subatmospheric pressure, subatmospheric pressure, and here we can say if the particular soil water is there, submergence force is also there, submergence force. And if the particle is here or rather here, we can say there is a pressure of atmospheric pressure, we can say pneumatic potential or pneumatic force. Pneumatic force. Okay, these are the major forces which develop in soil. So if we assign the potential value, it will be your potential terms. We can say the total water potential now. The total water potential, I am writing it as symbol. This is psi. Psi P is your total soil water potential. What are the components now? One is your Matric potential. And in case of saline soil, another potential comes, which I will write it as solute potential, or we can say osmotic potential. You can write psi S or psi O, rather I will write psi O because of osmotic potential. And I can write another type of potential that develop due to gravitational force. I can write, and another all these pressure forces like your submergence, pneumatic due to subatmospheric pressure, this type of forces I can write pressure potential. Now I think you clear the total potential in terms of different forces or different potentials. We can write this way. But if this is a non-saline soil, we can write this as Matric potential and gravitational potential. Sum of total water potential will be your in case of non-saline. This is in case of saline soil. Normally we consider this. I am neglecting here the pressure potential because this subatmospheric pressure and the submergence potential we are just neglecting to make the calculations easy and for convenience point of view. So total water potential is non-saline soil, we can see, is a sum of your Matric potential and gravitational potential. So among here we can see the most important force or potential which is acting is your Matric potential, because gravitational potential is your universal. So this is the most important. If you assign some signs, I can say Matric potential, okay, assigned will be negative sign. As you can see, here the potential was highest, and by entering this water through this force capillarity, this is capillarity. Entering through this capillarity, the potential is reduced, so the water will experience the negative potential, the battery potential actually on saturated side. Remember, this is on saturated side. This will be your negative potential. And coming to another potential, that is your osmotic potential. This is also negative side. Very clear. Now another potential, which is your gravitational potential. This I would say this may be negative, may be zero, and may be positive. How? Because we normally take a reference point. I think I am taking this as the reference point. Reference point. So how this reference point is chosen? Actually, it is chosen normally where the water potential is zero or maximum free energy of water is there. Okay. So if we are taking the gravitational potential above, as I have taken here, you can say it is positive value. Okay, from reference to above. If we lower the gravitational value, let's consider that is a saturated soil. I am taking the reference point above. Okay, and your gravitational potential just below there. In that case, the gravitational potential will be your negative. Very simple. Just try to understand it. And zero, if I take this gravitational potential here only, then this will become zero. This is very simple. Just understand this. Physics, if you understand things, this will be very long. This will be a very long-term memory. Okay. And now, among all these, if I want to define what is total water potential, total water potential, it is, we can say, the amount of work that is done. Okay, I am not writing, you just understand and note down yourself. The amount of work that is done to transport reversibly and isothermally. This is a textbook definition. Reversibly and isothermally. Why is it written? Reversibly means this process is reversible. Isothermally means we are taking the temperature constant. This is the total amount of work done to transport reversibly and isothermally an infinitesimal quantity of water. Infinitesimal quantity means very small quantity from a pool of reference level to a point on the soil water. This energy difference, I would like to take the water to this point. Okay, and you just always remember we will taking pure water because there will be no forces acting on it. The free energy or the maximum free energy is available. So we are taking from this reference point to this point simply the pure water. Okay, this remember. Just taking the water from here, the energy difference is known as your total water potential. Total amount of that work done, we have done. This is called as the total water potential. Very simple. And also I can say the potential energy. Okay, difference, potential energy difference. In terms of energy terms, I am saying potential energy difference between a reference level and point, the given point. Okay, you can say this is potential energy of pure water between a reference state and that of soil water. And that of soil water. Here you can write pure water. This is very simple way to remember total energy, total potential energy. Actually, this concept actually very much confused by students. So just try to understand here. This is very simple also now. I think potential energy difference of pure water between the reference state to a given soil water state. Very simple. Now, if you see this potential term, total water potential term, actually given in Gibbs free energy state, thermodynamics, Gibbs we can say, we can write the total amount of work done will be your function of force, different forces acting. So force against which the water is moved, and ds, I have said infinitesimal quantity of water and infinitesimal distance, means very small distance is travels in soil. That's why we also neglected the kinetic energy, we know. So that's why the differential term is assigned. These are the conceptual things you need to know. And your cos theta, this is the angle it creates with force fields during its traveling path. Very simple now. But as we are all these terms are expressing in terms of potential energy, you can write the work done will be your mgh. Simple. This is the height of rise in the plane rise. This is the acceleration due to gravity, and this is the mass of this your soil water. Very simple now. And actually, the first question I have forgotten to tell one important memory based, or you can say good question. Your all these soil water concept terms was earlier stated by Buckingham. The scientist name was Buckingham. He actually started this in 1907. He started all these concepts to express the soil water. Now, if you see, now you know what is soil water. Soil water potential, total soil water potential. Now, we want to know all the units. Everywhere, if we assign some value, we want to know how to measure, what are the units, how it moves, like this way. So, next we will see some units. If you see units of soil water potential, units of soil water potential terms, I have already expressed this in potential energy term. So, energy for your unit volume. You see, unit volume. What will happen? This volume is your density equals to mass by volume. So, in terms of this will become, this equation will become your volume will be mass by density. If I am keeping this mass and density value here, I can get rho gh. Okay, this is actually your soil water potential. Okay, this calculation actually your soil water potential. If you assign some units, we can say this is in bar, in atmosphere, in kilopascal, or rather I can say Newton per meter square. This is very simple, or Dye per centimeter square. These are the units. And if you see, in terms of your CGS unit, that is or per centimeter square, very simple. And you can also assign some dimensions. This is your homework. Assign the dimensions to these soil water potential terms. And if we calculate your potential energy per mass, we can see, find the value. This is GH. Actually, this is called as your chemical potential. So, the unit now becomes joule per kg. Okay? You can say, this is important. Just remember. And if you express this potential energy per unit weight, this is your potential energy per unit mass, per unit volume, potential energy per unit weight. This will give your H. This is called as hydraulic head. This will be most commonly used when we calculate the water movement in saturated and unsaturated soil. This will be most commonly used. Okay, this is very simple. The unit will be centimeter. And if you, I have already told you one concept, PF was there. Simply we can express also PF in terms of head units. Your PF value, I have told you that is PF, the force with which the water is held. The more force it will be held, the more will its value, and less quantity of water is available. Okay, more abrasive forces will be there. Log H, very simple. If the value of your hydraulic head is 10, then the PF value will be your 1. And here remember, this is base 10. This is not written. Sometimes you think this will be for base 10. Okay, this is PF value. Also, we can express these units. I have said we can. If you see some conversion factors, I can say 1 dyne is your 10 to the power minus 5 Newton. Okay, 1 Newton is your 10 to the power 5 dyne. Very simple. And in terms of bar, we normally express all these units of soil water potential in terms of these units. So that's why it is important to know all these conversion factors, so that we will calculate the problems and we will solve the mystery behind the soil water potential. This is, you can say, 10 to the power 6 dyne per centimeter square, and you can say 10 to the power 5 Newton per meter square, and 1020 centimeter of water column. Centimeter of water column. That I told na head unit. This is actually water column. 1 bar is equal to that. And in terms of atmosphere, 0.98 atmosphere. Okay, this is 0.98. Normally we take 1 bar equals to nearly equals to 1 atmosphere during expression. And we can say another bar is your 100 kilopascal. When we will calculate some problems, we will use this conversion factor most of them. Okay, now we have known what is soil water potential. Now if you see, we will see some concepts of water availability. We have seen the concepts of water potential. Now if we will go to different concepts of water availability. Concepts of water availability. Water availability. Okay. So in this concept, the first scientist who actually gave his hypothesis was Veihmeyer and Hendrickson. So if you take your transpiration rate, or you can say growth rate in y-axis, and you take what here soil water content. Here we say soil water content. Writing in short term, you can correlate. We are already discussing the soil water terms, so this is easy. And we say this is the permanent melting point, where water availability is 0, and this is the field capacity content, where the water availability will be 100%. And we draw between these your transpiration rate or with soil water content, will grade this type of graph. Okay, now we will try to understand this graph. This is actually very simple. Okay. So we can see the first scientist, I can say, was Veihmeyer and Hendrickson. in 1955. Earlier there were different schools of thoughts. They gave their hypothesis. In Veihmeyer Hendrickson in 1955, they thought the water content, available water content to soil, actually is of same between field capacity to your permanent melting point. The water availability is actually same between field capacity to permanent melting point. Then another school of thought came from scientist Thornthwaite and Mather in 1955 also. They also thought or hypothesized that the water content actually decreases from field capacity to permanent melting point in a linear fashion. As the water content, I can say in field capacity the availability of water is higher. As I am decreasing the water content from field capacity to permanent melting point, the availability of water is decreasing. And all the scientists that time were not satisfied. Then another school of thought came from Ritchie in their published paper in 1972. Okay, they thought or they hypothesized that if you apply some suction, okay, from field capacity, there will be no difference of available water capacity up to a certain point. I can say this is the point. Okay, this point there will be no effect, and after a certain point, the suction will be decrease the water availability from this point to permanent melting point. This is, we can say, threshold level, threshold point. So as per them, they told, that school of thought told that water content actually, if you applying small suction, will not decrease from field capacity to up to a certain point, that is called as threshold point. After that, the suction will affect the plant growth or your transpiration rate through availability of water. These are the schools of thought that time came. But actually, in field condition, we calculate this available water content. We calculate this available water content for a particular layer. You can say particular layer. Okay, dW. This is available water capacity for a particular layer. That is, I am giving dW. We calculate it as your field capacity minus permanent melting point into boil density into your depth of soil divided by 100. Actually, in this way, we actually calculate the available water capacity for the soil, and we know this is field capacity, the moisture content at this field capacity content, moisture content at permanent melting point, and this is your boil density, very simple. And ds is your depth of soil, 15 cm, 10 cm, like this way. This is the depth of that soil layer. If you calculate this depth for a single layer, and I want to also calculate for a full profile, so your available water holding capacity for a profile, I can say, which in terms of dp or profile. Okay, depth of soil water, or you can say available water holding capacity for a profile, this summation of dW. This way we can calculate the total water content in a soil profile. This is very simple. If you solve some problems, there are many problems available. This is on this concept. You just practice. Here I could have done, but the classes will become more lengthy. So that's why, if time permits, I will also discuss here some problems. And coming to another important sub chapter, we can say, it is soil, water, or soil moisture. You can say moisture, soil moisture characteristics. Okay, we are doing that SMC. If we try to understand this, we will draw a graph. In x-axis, here I am taking volumetric water content, and in y-axis I am taking metric potential, or you can say suction. In terms of metric potential or suction, you may take. I have already told you the major potential which is determining the water potential movement is your metric potential. So that's why it is rather easier for us to quantify or understand all these things in terms of metric potential compared to other potentials. Okay, and these are synonymously used with your suction and tension. We can say rather here also in some books this is written metric suction. You don't get confused. Okay, and if we draw the graph will come like this way. We can see different moisture potential values. The volumetric water content is different. Okay, here if you see the effect of texture, we have already discussed in soil physics. First starting point always we will do with texture. So if you see the effect of texture, I can say this is your thing, this is your the three type of textures we have discussed. One is your coarse texture, one is your medium texture, another one is your fine texture. I can say this is sandy texture, this is silty or medium texture, this is your fine texture. If I observe, I can say, if I am drawing the graph, I am seeing at a particular metric potential. Okay, particular metric potential value. If this is theta 1, this is theta 2, and here it is theta 3. I can see clearly that the water content is higher in case of clay soil, fine texture soil. We have already discussed developed due to the presence of more number of micropores, the water content will be higher in your fine texture soil. This is clearly evident. This is very simple to remember. Just remember this type of graph comes. So that's why when we quantify the soil moisture characteristics, we normally see it as soil moisture characteristics curve. Okay. In exam, it is most often asked question. What is soil moisture characteristics curve? You can draw this figure and compare with these different properties. You will see this actually is the fundamental property of water. This is the fundamental property of water. Fundamental property of water. And here you can see the values are coming in a curved way. That's why the curve value is as a curve was written. Soil moisture characteristics curve. It is not linear. This is very much clear now. Then coming to your structure, we can draw a graph also. In physics, everything we will try to understand through the graphs or problems. This is a like that way, that is metric potential or suction. You can say that is volumetric water content. Okay, and if you see, this is a compacted soil. Compacted soil, and this one is your aggregated soil. Aggregated soil. You can clearly see, just see a one memory type or you can say conceptual question. You can see at higher suction values, here the suction value is highest. We can say open dry soil. This higher suction values, your water content both for the compacted soil and aggregated soil is equal. Just remember, this is a very conceptual question which is most often asked. At very high suction range, the water potential value, or you can rather say the suction value is, or water content is same for both compacted and aggregated soil. And here we can also observe the high suction range values. If the high suction value like your permanent melting point, hygroscopic coefficient, then the texture of the soil most oftenly prominent. And if there is low suction, your prominent figure will be soil structure, because soil structure is mainly, we have seen the arrangement of different pore sizes. This is mainly affected by pore diameter or pore size distribution. Okay, so that's why always remember this point. This is also one important point. At higher suction ranges, the effect of texture is more prominent compared to your structure. But at lower suction ranges, the effect of structure will be your more prominent compared to structure. Texture. Now, another important phenomena occurs due to this soil moisture characteristics called, we say, hysteresis. This is also important concept. This hysteresis concept. This is also very important. You can say hysteresis. Hysteresis. What happens in hysteresis? Let's draw a diagram to understand this concept also. As we have seen, this is matric suction. This is your matric suction, and here it is your volumetric water content. Okay, and if you draw the curves, we have already seen. And what happens? You see, one initial oven-dried soil is wetted. Your initial oven-dried soil is wetted. So after wetting, the curve will come this way. Okay. You can say this matric suction ranges. This is oven dry. I am writing 1000 bars. Okay. And in terms of matric suction, I am writing that is positive. If you will write in matric soil matric potential value, okay, then we will write it negative, very simple. And if you are wetting, this type of curve comes, we can say wetting curve. And also we can say it is absorption curve. And that same soil now wetted and will be drained out. All the water will be removed. Still, the water, the curve comes this way. This is your drying curve. Okay, we can say desorption curve. We can say same soil which is wetted contain less quantity of water. If you draw this type of thing, you can see the water content during drying. Volumetric water content during drying is higher compared to the volumetric water content at your wetting curve. So this kind of phenomena is actually hysteresis. Hysteresis here is very simple if you want to define. This is the desorption curve. Okay, the different quantity of water content during the desorption curve compared to the wetting curve. Their difference is called as simply the hysteresis. Very simple. You don't need to mug up all those definitions. Draw your graphs from that you can define yourself. Okay, this is very simple. And also there are development of different scanning curves. This is wetted, this is dried. Let's say this is wetting, this again is your dried, and this is another scanning curve. This is wetting, this is dry. Actually, in normal field condition it also occurs. If the soil is dry, very much dry, now rain or precipitation or irrigation happens. So what will happen? The soil will get wet and the evaporation happens. What happens? The normally soil dries up. You will observe if the rainfall happens, there will be earlier some pores will be there. So the water content will be less compared to when the earlier filled soils or wetted soil will dry through evaporation or natural process. This is I am saying natural process. We done this actually laboratory by oven drying this process. Here you can assign different values, potential values. And here another important point, you just remember, this is, we can say, air entry value. Air entry value. To understand this, you just think when a fully saturated soil is there, you will apply some suction. As I have said, you will apply some suction. Then the volume of water content will not change. But after applying more suction, the volume content will be changed quickly. So this value is actually called as the air entry value, or you can say this threshold limit. After reaching this threshold limit, when the water, after giving more suction, when water removes, this will be called as your air entry. And why this scanning curves? You are also seeking why this scanning curves. Then this scanning curves, actually in your soil, you normally not get always the saturated soil or dry soil. You get partially wetted soil or partially dry soil. That's why the scanning curves are asking. Now very much clear. Now hysteresis is very much clear. Now if you see what are the factors then affecting this hysteresis, this is also important. What are the factors affecting? If you say the first factor is your ink bottle effect or ink bottle effect, or we can say non-uniformity of pores. Non-uniformity of pores. Again, we will draw some pictures to understand this concept. What happens? Already I have told, if this is your pore geometry actually in like that way. There will be a macro pore. You see, this is a macro pore, and there are small micro pores. And you can see this whole structure is looking like a ink bottle. We are not using nowadays ink bottle. Earlier, actually, it was used. And we can say this is its body, and this is its neck. If we want to draw, here we will draw. This is a ink bottle. There will be your neck and your body. And you can see this is the soil water. This is, you can say, this is A and B. A1 is your drying curve. Okay, and this type condition is wetting. This kind of condition is observed in your wetting soil. So what happens? You can normally see as it is here as an ink bottle. We can say this is its body and this is its neck. If earlier the soil is saturated, we are applying some suction. So what will happen? The water will remove from this portion, from first neck, then after from the body. So this is earlier saturated. So this will take more time. If a particular matric suction, if you are seeing matric suction or potential, okay, you can see the water is already in their body. But in a wetting soil, if you are wetting, this is a earlier dry soil, you are wetting, this particular matric suction, this will pass, the water will pass through this neck portion, then will reach body. So it will take time. So at a particular matric suction, we can say the drying curve has more water content compared to a wetting curve. This is actually due to the non-uniformity of your pores, or called as ink bottle effect. Now try to understand another concept, which is contact angle. Thus try to understand all these concepts. Will be very much easier for you to remember. In contact angle, if you think this is a solid surface. Okay. Now a water bubble comes. or rest here, you can say, and it will make some angle. This is your solid, their surface tension will be developed, solid and gas. Here it is gas. Okay, here the surface tension will be your gas plus liquid, and this is water. This is angle created theta. You can say contact angle, and here the tension will be your water and solid. Water and solid. So if you see, as per the Young's equation, this your gas solid surface tension of your gas liquid cos theta plus your surface tension at liquid and solid. This is very simple. Now from cos theta you will see the surface tension by your gas and solid minus surface tension of liquid solid and surface tension of GL. Actually, this is the contact angle equation. From this, actually, we can observe the hysteresis, but it will be difficult. Let me understand you in a other way. I thought this will be easier way, but you will get confused. Another simple way we will try to understand. You can see this is a soil surface. Earlier, the water is like that way, and it is making angle, but here the what is contact angle actually? You know contact angle, na? That is angle formed at the interface of your air, water and gas. Very simple. This angle formed at the interface of air, water and gas. Here the water is there, gas is there, and this is solid. So this will be angle cos theta. Here you can say theta is your 90 degree. That is dried soil, and fully dried soil you can say theta is 180 degree. Fully dried soil. Your fully dried soil. Now as the time passes or wetting happens, what will happen? The contact angle will reduce. Now you think the contact angle is 45 degree. Now the contact angle is 30 degree. When the soil is fully wetted, now there is development of no contact angle. So we can say your contact angle is 0. Now from this actually you will be better understand what is hysteresis happening due to contact angle. You can see during dry, this is wet. Okay, so you can see the contact angle is actually decreasing with wetting, and the dry core was actually more quantity of volumetric water content compared to this wetting core. From this only you can observe these are the contact angles. Okay, this is very simple now. To observe this figure, you can clearly see that due to the effect of contact angle, there will be development of hysteresis. Another few factors affecting your this hysteresis, I can say your swelling and shrinking. Swelling and shrinking. If you understand first two factors, then these are very easy. As you know, these are interconnected pores will be there. If swelling and shrinking happens, earlier there will be pores. So during wetting, some pores will be remain also air pockets will be remain there. So this will create hysteresis. Very simple. And another one is your entrapped air. Entrapped air like that way I explained. If air but dry soil is there, you are wetting. There will be earlier some all the pores containing air will not be removed. So some entrapped air will be inside them. That will cause hysteresis. Always remember the drying core acquires more volumetric water content. This way you can easily characterize all these things or factors affect. Also presence of different organic matter etc. These also affect the hysteresis. Now we have known soil water potential concept, soil water availability concepts, all these concepts.